Hi everyone, this is Madhav. We are back at this again with physics, and we have a big, ugly question here that looks very complicated with very many colors. We have this block over here, and we have a second block over here. What we're gonna do is we're gonna make the block slide down a ramp and go across like a rough patch before it has a big collision. After the collision, this second block, it's gonna be either the only block to keep going forward or the block that's going forward faster. So depending on whatever case it is, after the collision it's gonna go up this loop-de-loop, barely make it to the top, and based on that condition we have to work our way all the way backwards and figure out what is the initial height that we need to release this block from, at the very least, in order to make this possible. This is a long problem. I'm not going to say it's the hardest problem in terms of concepts, because roughly we can visualize what's happening a little bit, you know. The only issue is that there's so many different steps, and that's why I color coded everything based on all the different steps, so that we could figure out and work our way through a bunch of simpler problems that we do know how to deal with. You know, we know how to deal with a block going down a ramp. We know how to deal with a block just going over a frictional surface. We know how to deal with a collision between two blocks, and we know how to deal with a block going in a loop-de-loop. It's just harder in terms of the amount of information coming at us when we consider all of it at the same time. So that's why we're gonna break this problem up, as we always do, and solve the smaller, simpler problems one at a time. First, of course, let's make sure that we're understanding a few assumptions we're making, especially about whether we need to consider the height of the block, because we're going to be using some energy conservation equations that include gravitational potential energy, whether or not we need to consider certain objects in our equations, where friction actually exists, and which types of other non-conservative forces do or don't apply. And of course, we have the biggest assumption. We need to assume that the collision is perfectly elastic, because you know that's kind of the only thing we know how to deal with, otherwise we'd be pretty stuck. So yeah, we have to take all of these assumptions of the problem into consideration. Now, before we go into any very detail-oriented things, you know, let's just think intuitively about what's going to happen. So if we have this block that is sliding down the ramp, it's going to be slowed down when there's friction, right? When there's a perfectly elastic collision, energy can't be lost, so it's going to be slowed down, but like we still have another block to keep going with some of the energy, maybe all of the energy, we don't know yet. And of course, when it goes over the loop-de-loop, then it's going to be slowed down, because you know it's trying to go uphill. So what we should expect is we need to increase the heights if we have more friction, or this thing has like a higher ending position, which is related to the radius of the loop-de-loop. So we should expect to see some terms related to these things in our final answer. Just like a rough intuition, right? So with that being said, with a rough intuition out of the way, let's dive into the details. First of all, we're gonna do our Grass analysis given required analysis, and then we're gonna do the solutions and solve stuff later. But we just wrote down everything we knew and what we needed in terms of the final variable. As I explained, I'm gonna break it down in steps, and yeah, we just had a few more assumptions to take care of. First thing, in black, sliding down the ramp. This isn't, the worst thing. We just draw a free body diagram. And in this case, we don't even end up needing this, because it's simple to just figure out what is the final velocity by using an energy conservation equation, because there's no friction on the ramp. So we have no change in energy because no friction, no other non-conservative forces. We expand that into both the kinetic and gravitational potential energy changes. For the kinetic energy, the subscripts might be a little bit confusing here, but just visually, starts off with no energy, starts off with no kinetic energy because the block has no velocity, so that's the starting condition, and then it ends up with some energy. Conversely, for the gravitational potential energy, at the start it has some potential energy because it's up high, it ends up low, so then it doesn't have energy, gravitational potential energy. We cancel out these terms because, being multiplied by a zero, they just end up being zero. And we have this left, which lets us isolate for the velocity at the bottom of the ramp, which is what we want. Because now that we have the velocity at the bottom of the ramp, we can figure out, okay, this was some starting velocity and now it's going to lose some energy as it goes through friction. So there we go, that's a quarter of the problem done. Next we go to the frictional case. Again, it's not too difficult, it's just break it down, let's just chug through it. So again, we have a free body diagram. You can see that we have some initial velocity going rightwards and we're going to have some friction slow us down. So as usual, when I have a bunch of equations, multiple axes, I like to create a table of equations because it helps me just not get lost in all the writing. On the y-axis first, this direction, we see that if we use Newton's second law, I'm just writing this out explicitly once, if we use Newton's second law and sum up the equations on the y-axis, then we have the normal force in the positive axis, we chose this to be positive, and the gravitational force in the negative axis. Of course, there's no acceleration because the block's not sinking through the floor, it's not rising up, so we just set these things to be 0. In the x-axis, we only have the frictional force. We know that in this case it's kinetic friction because the block is sliding, and so we just put in that formula for kinetic friction. Finally, we have this energy conservation equation because we know some energy will be lost to friction, which is why we have a negative sign in terms of the change in energy. Don't forget the negative sign, it's going to screw up our answer later if you do, because that's what I did, so don't do that. Finally, we know that the work done by friction, it's, force times distance. That's the definition of work. So using all this, we're now ready to substitute stuff around so that we can figure out how much energy is lost, which will tell us what the velocity is at the end. So from this wonky mess here, I just simplified stuff and I figured out that the normal force, it was proportional to the gravitational force. I substituted that in here, and then I took this and I put it in here. Here we are. And then I took this and I put it in here. Yeah. Finally, I expanded, the change in energy in this case refers to the change in kinetic energy because there's no changes in gravitational potential energy. It's just sliding along a flat surface, so its height doesn't change. And so when I expand that out a little bit, again, mess with subscripts, I just clean this up a little bit and divide by mass on both sides because I can get rid of that term. Multiply by 2 on both sides so I can get rid of this 1/2. And now this is looking a little bit better, especially because I can isolate for what I really want, the final velocity, and I already have, found an expression for this term in the last part. So that's all I need. I isolate for everything, and now I can just make the substitution I wanted, clean it up a little bit, and I get, the final velocity of the block. If the equations seem like a mess, just remember block was moving at a big speed, then it slowed down, and now it's here. Now that it is here, now it's time for the block A to collide with some other block B. And the special thing about this collision is the two blocks, they have the same mass, which is going to give us a special property that you'll see. And the other thing is that it's a perfectly elastic collision, so we know that both linear momentum and energy must be conserved. So now we're, halfway done our problem. Let's move on to the second last section. So when we have the perfectly elastic collision, we only have two equations, right? One for what I just said, energy conservation, and other for the other thing I said, which was linear momentum conservation. These two equations, they seem a little bit similar, right? And note that I just left out, the velocity of block B at the beginning in both of these because it was 0. We know that. These seem similar though because MV, MV, MVF, MVF, and so on. What if we just divide this equation by this equation? I did that, and you just have, this mass and mass cancel out, mass and mass cancel out, and these squared terms cancel out. So this is much neater. We can also multiply both sides by 2, left side and right side, gets rid of these fractional terms, and now we have a pretty simple equation. It just says the velocity, it's going to be combined in terms of the velocity at the beginning for block A, velocity at the beginning of block A, it's going to be distributed into the velocity for block B after the collision, and whatever velocity A has left, if it has any left. Don't get lost in the subscripts, keep looking at the pictures. It helps me after pages and pages of equations. So anyways, I isolated for the final velocity of block A by just, subtracting VBI from both sides. And I substituted this back into this equation. So where it said a VF, I instead put in VBI minus V, as you can see here. This lets me isolate and, collect rat-like terms. This MVBI, they add together. I have 2 MVBI, and then M distributes to V. Add these on both sides, and divide by 2M on both sides. And now notice the implication of what this means. Again, don't let the subscripts confuse you. What this is saying is the velocity, the initial velocity of A is the same velocity that B has after the collision. That's interesting. Okay, So what that means is if we substitute this back into our equation up here, then we're just taking VBI and then subtracting VBI, which means the final velocity of block A is 0. So to draw this out, initially A was moving and B had 0 velocity, they collided, and then after A stopped moving and it transferred all its velocity to block B. This is going to happen whenever we have a perfectly elastic collision between two blocks of equal masses. They're going to be able to transfer all the energy from the moving one to the other one. So this is just a bit of intuition to keep in mind. Anyways, all of this complicatedness is just to say that the velocity we need for block B continuing forward in this problem is just going to be the same as the velocity we found in the last part here. Okay, again, context. So block A, it fell from some height, had some velocity, lost some due to friction, didn't lose any in the perfectly elastic collision, just, well, it lost it, but it transferred all of it to block B. So now we can just ignore the collision, because all we care about is block B is going through this last loop-de-loop part, and we want to figure out how that affects the loss of energy, because it's going to lose some energy. The kinetic energy in particular, it's going to gain gravitational potential energy and lose kinetic energy because it's going up a hill. So let's go to this last part. Here we see a very talented drawing of the box going around the loop-de-loop. I just did a zoom in of the top bit and drew a free body diagram, where in this case the question said the box barely makes it to the top. And what that tells us is that, okay, if it barely makes it to the top, that means that it's just about to lose contact, it's just about to fall off the surface of the ramp, the loop. And if it's about to lose contact, then you cannot have contact forces. Pretty evident, right? And the normal force is a contact force, so you cannot have a normal force in this case. The other thing to note is that this direction downwards is the same direction as the direction to the center of the loop. So whatever acceleration we have in the y-axis is going to be the same as centripetal acceleration. So given all of these hints, what the question's really telling us is, hey, start thinking about dynamics, start thinking about circular motion and centripetal acceleration, and start thinking about energy conservation because you have no friction but a change in height. And so based on that, these are the three equations I created. So over here, this is from Newton's second law. This is just, the net force. It's just mg, no normal force. It's equal to ma, in this case in the y-axis. And ay is the same thing as centripetal acceleration, so I just used the formula for centripetal acceleration. Now, we can simplify equation 16 by just dividing both sides by m, and we get g is the only source of acceleration because you only have gravity pulling it down the block at the top of the loop. Now we can take this and substitute it in here, isolate for VBF, what is the final speed of the block, and here we are. Finally, we can take this and substitute it into our energy conservation equation. Again, don't let the subscripts, get the hold of you. The block B has some final velocity, it had some initial velocity. We have formulas for both, so we're good on that end. It has some final height, which is 2 times the radius, right? Because going to the radius would get you halfway to the top. Then again to the radius gets you all the way to the top. So the height is 2 times the radius, assuming that the height of each block is negligible. and before it was just at ground level, so there was no uh, gravitational potential energy. The height was 0. So we just cancel out this term and we're left with these things. We also divided all of these terms by m so that we wouldn't have to consider the mass. Now I did what I just said. We have determined equations for each of these velocities, so we just substitute them in. Over here we just end up with gr. Over here we have like this complicated mess. We're going to divide everything by g, and these two things cancel out, 1/2 times 2, so we have 1/2 r, and then the stuff up front's cancelled out here, and then we're left with 2r because we divided out g. Let's clean up this negative negative, turn it into a positive, and then this negative also distributes over hi. Also, I collected 2r and 1/2 r to make 2.5 r. And finally, long time later, we can just add hi on both sides of the equation and we are done. We got exactly what we expected. If the radius increases, then we're going to need to increase the initial height of the ramp to compensate. If the friction increases, either because the coefficient of friction increases, so you have a more rough surface, or you have the friction being applied over a longer distance, then the height also increases. And finally, we can substitute in our values that we were given up top. No worries if you don't remember them, we just get this final answer. This also makes sense because, signs are positive. The units here are, the radius is in meters, df is in meters, the distance that the friction is applied over, and 2.5 and mu k, the coefficient of kinetic friction, they're unitless. So the end answer here ends up being meters plus meters, or just meters. So the units make sense too. So this seems like a reasonable answer. And here we just broke down a very, very messy path.